Hello everyone, welcome to the Arithmetic Zone. Today we have a video for you guys on the AP Calculus AB 2019 free response questions. Now, I just want to go over some quick disclaimers. This will be a long video. There's like no way around it. We're going to go over all 6 questions that are involved in the AP Calculus free response questions for the AB course. And so we have in the description timestamps of all of the topics that are covered by each part of the question so that you can just skip ahead and go to whichever portion of the calculus class that you feel that you're not so confident in. And additionally, this took a lot of prep to go into. I have a set of pre-prepared notes. I've gone through these questions multiple times in order to solidify my understanding to give you guys the best quality content. So I really hope you guys enjoy this video as this took a lot of work. So this is going to be section 2, part A. Part A is going to be calculator active. You're allowed to use your calculator for all portions of the question. Section 2 just corresponding to the free response. This is going to consist of 2 free response questions, and you get 30 minutes for each. So you kind of want to, on test day, spend about 15 minutes per question. And then afterwards, you're going to go on to section 2, part B, in which it is non-calculator, in which you cannot use your calculator for any portion. You can go back and forth between the sections once you get to part B, but you will not get your calculator back. So it is suggested that you finish these 2 questions within the first 30 minutes. Now, each free response question is set up in a way where they'll give you a stem. In this case, that's this portion right here that applies to every part of the question, which is usually like 3 or 4 parts per free response. So this is going to be our stem, and you can read that if you'd like. I'll just go on to the portion that we're going to answer. So this is going to say, how many fish enter the lake over the 5-hour period from t equals 0 to t equals 5? Give your answer to the nearest whole number. So we're given a rate function with how many fish enter the lake, with fish entering the lake at a rate modeled by the function e. And integrating a rate function will yield a total, and that's where we're trying to find the total number of fish that enter a lake. So that's what we're going to do. We're going to take the integral from the specified bounds from 0 to 5 of the rate function e of t dt. Now, the nice thing about the calculus exam is that if a function is already defined for you, or you've explicitly stated what the function is equal to, in this case, e of t is given by the problem stem, you don't have to rewrite what the function is equal to. You don't have to write 20 plus 15 sine and that stuff inside of the integral. You can just leave it as e of t. And because this is an approximation, we're going to round up to the nearest whole number. We're going to use this notation of the equal sign, the squiggly equal sign, and that's going to be equal to about 153. And I'm going to say fish because that is our unit. Now for B, what is the average number of fish that leave the lake per hour over the 5-hour period from t equals 0 to t equals 5? So this is actually an important formula that I suggest you remember for test day. It's going to be 1 over b minus a times the integral from a to b of your function with the appropriate differential. So in this case, our a is going to be equal to 0, our b is equal to 5, and then we can just substitute appropriately. It would be 1 over 5 minus 0 times the integral from 0 to 5. And we're looking at the average number of fish that leave the lake. So instead of using the e function, we're going to use L because that is the rate at which fish leave the lake. So I'm going to put L of t. Again, I don't have to put that 4 plus 2 to the exponent stuff. And that's going to be equal to 6.059 fish. I don't really like this notation. Oh, it'd be fish per hour, excuse me. I don't really like this notation of saying 6.059 because you can't really have a decimal number of fish. But unless the College Board explicitly states to round your answer to the nearest whole number, you should leave it rounded to 3 decimal places, as that is the rounding rules that they have put forth. Now for C, at what time t for 0 is less than or equal to t is less than or equal to 8 is the greatest number of fish in the lake? Justify your answer. So to find the total rate of fish in the lake, we're going to have to establish a new function. I'm just going to say that this new function is equal to f of t. You can realistically name it whatever you would like, as so long as it's equal to e of t minus L of t. This is our total rate, because we are subtracting the number of fish that leave from the number of fish that enter to give us the total. And because this is, we're trying to find the greatest number of fish in the lake, we need to find the derivative of the rate, or not the rate function, of the fish function, which would just yield the rate function. And we already have the rate function, so we don't have to do anything in terms of differentiating. We're just going to set it equal to 0 and find critical points. So I do think that in this case, it is appropriate, or rather helpful, start in the values of e and t and L of t. So I'm going to do that right here. We're going to have 20 plus 15 sine of pi t over 6 minus, you want to put the parentheses, you don't want to mix up you want to be very careful with notation. And so now you would just put this into your calculator and find the intersection point that conforms to the interval in the question for where the graph crosses the x-axis for where x is, or rather t is equal to 0. And you want to look for when the graph goes from positive to negative, because that's going to indicate a maximum, which is what we're trying to find. And so if you do that, you would get that t is equal to 6.204. And so our justification, this is going to be the time where there's the greatest number of fish in the lake. So our justification is going to be f of t is greater than 0, aka it's positive, over, and it's going to be from 0 to 6.204. You want to make sure that this is a soft bracket because that's not a part of the interval, because at 6.204, the function's equal to 0. And f of t is negative or less than 0 over, again, this should be a soft bracket, 6.204 to 8, comma, therefore, the greatest number of fish, you want to keep it in terms of the problem, and you want to use the language that the problem uses in order to maximize points. In the lake is at time t is equal to 6.024 hours. Now, I know in the previous question, they tell you what time t equals 0 corresponds to, like t equals 0 is midnight. So I guess you could technically say that t equals 6.204 is something like 6 a.m., something around there. But I feel like it's much more safer to just state the t value instead of trying to find what it corresponds to with the context of the problem, as the College Board will accept both answers. Now D. Is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m. t equals 5? Explain your reasoning. So again, we're going to look at this function. I'm not going to write it out again. We're going to look at e of t minus L of t, because we're trying to look at if the total is increasing or decreasing at t equals 5. So I can actually just get rid of this t and rewrite it as e prime of 5 minus L prime of 5. And you don't have to take the derivative by hand. Taking the derivative like this does not seem pleasant. So that's why this is calculator active. You just need to show the process of what you're putting into your calculator. So for e prime of 5, you're just going to take the derivative with respect to t of e of t when t is equal to 5. Again, you don't have to rewrite this whole expression in this portion. As long as you put in your calculator correctly, then it should be fine. Minus ddt of L of t when t is equal to 5. You're finding the derivative at a point because you want to see whether it's increasing or decreasing. And this difference should give you approximately negative 10.723. Express your answers with at least 3 decimal points. You can put more numbers in your question. They will stop at the 3rd decimal point though when checking for accuracy. So now that we have a final answer, we need to interpret the meaning of this derivative in context. So I'm going to say that since e prime of 5 minus L prime of 5, I'm going to put this whole thing in parentheses because I want to say that this whole thing is less than 0. It's negative. The rate of change. I'm going to use the wording of the question one more time like I did last time. In the number of fish is decreasing. You don't need to go ham with the explanation. It could literally just be this one sentence and it would be sufficient for full credit. Now, the second question. We have this stem again. It gives you some information, and we have this table of values. And now we have this question A, the first part of the question. So we're going to justify why there must be at least one time for 0.3 less than or equal to t, which is less than or equal to 2.8, at which the velocity of particle p prime of t, the acceleration of particle p, equals 0 meters per hour per hour. Now, this wording lends itself to using an existence theorem. So when I look at this question, I think of mean value theorem, but I feel like you could use Rolle's theorem if you wanted to, but it's not addressed explicitly on the scoring guidelines. So let's just go with the mean value theorem, which, if you forgot, I do think it is worthwhile writing again. It's f prime of some number c is equal to f of b minus f of a over b minus a, basically stating on a closed interval, there's going to be at least one point in which the derivative or the slope of the tangent line is going to be equal to the slope of the secant line or the average rate of change. And for this to be true, function must be continuous and differentiable. If these two conditions are not met, then the mean value theorem does not apply and you cannot use it. Luckily for us, they give us that the velocity of particle b is given by the differentiable function bp, and differentiability implies continuity, so we are set to use the mean value theorem. So we're just going to do exactly that. We're going to say that vp prime of t, using the function that they give us, is equal to vp of 2.8 minus vp of 0.3 over 2.8 minus 0.3. And this is equal to, well, the value of BP at 2.8 is 55. It's also 55 at 0.3. This is over 2.8 minus 0.3. We're going to have 0 in the denominator, so it doesn't matter what or rather, we're going to have 0 in the numerator, so it doesn't matter what it is in the denominator. It's not going to be indeterminate. It's going to be 0 over some constant. So we get that BP prime of t is equal to 0, meaning that yes, there will be at least one time t over the interval where the acceleration is 0, and you do have to write a written explanation. So I'm going to abbreviate, but I'm going to say because the function is continuous and differentiable, over the given interval. You could be more specific and explicitly state what the interval is. The mean value theorem can be applied. You don't want to abbreviate and say MVT. You want to literally write out the mean value theorem can be applied. And I'm just going to continue my explanation over here with the star indicating where it stops and ends. It guarantees that there is at least one time, it's not one point, it's one time t where the acceleration of the particle P is 0. Now, I apologize for the sloppiness of that. You're obviously going to be given much more space on the day of the test than I do right now, but your answer choice, or not answer choice, your answer should conform to what I have here. Now for 2b, we're going to be using some Riemann sums. We're going to use a trapezoidal sum to be specific, with 3 subintervals to approximate the value of the definite integral from 0 to 2.8 of Vp of t dt. So the general form of a trapezoidal sum takes from the area of a trapezoid, which is going to be equal to 1/2 base 1 plus base 2 times the height. And so the bases are going to come from this VP, the bases are going to come from the VP section, and the height is going to be the time interval from where we took the bases. So let's just write it down here. The integral from 0 to 2.8, the VP of t dt is approximately, you have to use those little squiggly equal sign marks in order to say that it's an approximation. If you use the solid equal sign, you're going to be marked wrong. Or if you don't want to have to worry about that, don't write this statement at all, just go in with your math. So let's go. We have 1/2 times, we're going to take from the two bases, 0 and 55. So that's what we're going to write, 0 plus 55. And then our height is going to be the difference of 0.3 and 0, which is just 0.3 plus 1/2. Again, we're taking from our bases, 55 and negative 29. So adding them, well, it's really subtraction, and then the difference from 1.7 and 0.3 is going to be 1.4 plus 1/2. Again, taking from our bases, negative 29 and 55. And then the difference in the time interval is going to be 1.1. And that is our 3 subintervals. And this whole thing is going to be equal to 40.75. And we want to be specific with what this represents. This is going to be, the integral of velocity is going to be the position, which is given in meters. So the distance traveled from 0 to 2.8 is approximately 40.75 meters. Now for 2c, we have a second particle q that also moves along the x-axis, so that's velocity over the given interval is given by that function in meters per hour. We're going to find the time interval during which the velocity of particle q is at least 60 meters per hour. We're going to find the distance traveled by particle q during the interval when the velocity of particle q is at least 60 meters per hour. So that was a lot of words, and actually this is such an involved question. I gave myself an extra slide to do this. So for this question, I'm going to just rewrite what dq of t was given to be, which is 45 root t cosine of 0.063 t, or rather t squared. I think that is correct. Yeah. And so when we want to find the point, we want to find the time interval during which the velocity of particle q is at least 60 meters per hour. So we want to find the t values when dq of t is 60. So I'm just going to write 60 equals, and then this whole thing I'm going to bring down here. And now this is time for the work of your calculator. You want to find the intersection points of these two equations, because 60 is in itself an equation. So y1 would be 60, y2 would be that function. And you want to adjust your window because usually the mins and maxes are negative 10 and 10. And obviously if we're dealing with 60, you need to adjust it so that you can see where the intersection points are. And so like if you were to graph this on your calculator, we're going to say that this line is going to be the graph y equals 60, and the graph of VQ of t is going to look something in the ballpark of this. Obviously, it's not going to be perfect. Your graphing calculator will make it look better, but it's going to look something like this. And this is why you really need to watch your interval. You only want to focus on when the graph of V is above 60. So really your interval of focus is this region right here. And so you want to find your intersection points here, at this point, and at this point to give you the interval. And you're going to get that t is equal to 1.8661815, and that t is equal to 3.5191744. Now, for every other question, I've been rounding to 3 places, but there's a reason why I didn't for this question. Because the second part of this, part C, is to find the distance traveled by particle Q during the interval that we found here. And so that is going to involve an integration with these two t values serving as our bounds of integration. And so rounding it, we don't want to cause any discrepancy when doing the integration and putting it into our calculator. So we want to leave our answer as accurate as possible with no rounding. We're going to round our final answer. And so a little trick, I'm actually going to set this value equal to a, the variable a, and this value equal to the variable b. So now when we find the distance, when we integrate, I can just say this is going to go from a to b instead of writing out that long line of decimal values. And it asks for the distance traveled by particle Q, meaning that it wants the magnitude. It doesn't want the displacement. And so that means we're going to use an absolute value sign. You have to use the absolute value. And then we're just going to plop in what the Q of t is equal to. Again, you could just put VQ of t within that absolute value. But in my work, I have it like this, so I'm just going to stay consistent. And this should just go straight into the calculator. You don't even want to attempt to do this on your own because this is horribly disgusting. And so this is going to spit out an answer of about 106.109. And so I'm just going to write a nice little statement to kind of wrap up all of the work that we did here. So we're just going to write particle Q traveled a distance of 106.109 meters during the time interval and this is where setting our t values equal to those variables is going to help. A, B. We've explicitly defined what A and B are equal to, so we can say that in our final answer. Cool. Now for the final part of question 2. At time t equals 0, particle Q is at position x is equal to -90. Using the result from part B and the function VQ from part C, approximate the distance between particle Q or P and Q at time t is equal to 2.8. So this one's kind of a doozy because we're going to have to use the different components from B and C. And so in part B, we've said that the approximate value of the integral from 0 to 2.8 of VP of t dt is equal to 40.75 meters. So I kind of just want to focus on that when doing part D. We're going to take this integral from 0 to 2.8 of, x of particle P, the position of particle P at 2.8 is equal to 40.75. That's just a quick fundamental theorem of calculus from our part B answer from the trapezoidal sum. And now we want to find the value or find the position of particle Q at time t equals 2.8 in order to find the distance between them. We want to subtract their positions in order to find the distance. So we already know particle P, that was found in part B. So I'm actually just going to move this up here, make it a little smaller, just so that we have space for particle Q. We're going to take the same integral from 0 to 2.8, but instead use the function for particle Q. And we're going to use a bit of fundamental theorem of calculus. We're going to say that this is equal to the antiderivative of v of q, which is x, its position, at 2.8, minus x of q at position 0. And that's why we're told that at time t equals 0, its position is at negative 90. So I kind of just want to rearrange this. We're going to get x of q at 2.8 is equal to x of q at 0 plus this integral right here. So we're just going to plop that right in there. And that is straight to the calculator because we know what the function is equal to. And we know that x of q of 0 is equal to 90. So if you just do negative 90 plus math 9 and do the integral out, we get that xq of 2.8. It's the position of particle q at time 2.8 is going to be equal to 45.937653. This isn't the final answer, which is why I kept that string of decimal values. And so now we're going to approximate the distance between the two particles, meaning that we're just going to subtract. We're going to take this value right here. We want this to be a positive number, so we're going to subtract the smaller number from the larger number. So I'm just going to take this, make it a little smaller, and then we're going to subtract 40.75, and we get an answer of about 5.187 if you put it in the calculator. And so just writing a nice little statement to kind of tie that together, we can say that particles P and Q are 5.187 meters apart at time 2.8 hours. T is given in hours as shown by the graph, so we'll just leave it like that. And that's it for question 2. Now we're moving on to section 2, part B. This is what I was talking about, no calculator. So at this point, you're going to be asked during the test to put your calculator under your desk or just away. So now we're just going to rely on arithmetic. And this is where one of the beauties of the AP exam kind of come out, for calculus specifically. This isn't an AP arithmetic exam, or you're not being tested on how well you can simplify things. You're being tested for your knowledge of calculus. So you can leave some answers unsimplified. So now let's just get on to question 3. We're given the graph of f, and we're given the stem. And we will refer to the information in the stem a bit later. But for each subsequent question, I'll just have an image of the graph there. So question A is a question testing your knowledge of definite integrals. So we're given if the integral from -6 to 5 of f of x dx is equal to 7, find the value of the integral from -6 to -2 of f of x dx. And we're expected to show the work that leads to our answer. So we're going to break apart this initial integral. We have the integral from -6 to 5 f of x dx, and we're going to split it to yield from -6 to -2 of f of x dx plus integral from -2 to 5 of f of x dx. Now there's a reason I did this. It's because we know the value of this guy right here. Excuse me. We know the value of this guy right here. It's given to us as 7. And we can find the value of this integral right here because the integral of f of x dx from -2 to -5, well, we're given the graph of f and it's from -2 to -5. So we can find the value of that definite integral geometrically. And so we can find out these two values. So in reality, we only have one unknown, the unknown that the questions asks us to find. So I'm actually just going to rearrange some of these integrals in order to make it look more, to make solving it easier, I should say. we're going to have this is equal to, and this is just a simple rearrangement. We're going to take this guy right here, and we are going to subtract it from this guy right here. Cool. And now we're just going to sub in what we know. I should have just taken this guy and put it down here. I apologize for not doing that. So the integral from -6 to 5 of f of x dx, we're given that that's equal to 7 minus, and I'm going to put like a big bracket here just to section off this geometric area as it's going to take a bit. Now, I do want to point something out. So when a segment of area is above the x-axis, it's going to be positive. And when a segment of area is below the x-axis, it's going to be negative. So when looking at this graph, this triangle right here and this triangle right here, they have the same exact area, but one is positive and one is negative. So they're going to cancel out. It's the same story for these triangles right here. Those shaded red triangles, they have the same area, but one is positive and one is negative. So they don't factor a role into the total area of the graph over the interval -2 and -5. So if we want, we can actually just section off the graph. We're going to focus on this interval from 1 to 5. And so we're given this, I'm actually going to highlight this in a different color. We're given this kind of like trapezoid area right here. And we're given this weird like curve-like shape here. You might think you can't solve that geometrically, but with the properties given in the stem, we actually can. So let's focus on this orange segment right now. It's a trapezoid. So we're going to have 1/2 times the height of our bases. So that's going to be 1 and 3. And then, or rather, that's going to be our bases. And the height of the rectangle is going to be 1. And now we're going to add whatever area the green signifies. So we're given that it's made up of 2 line segments, that's these 2 portions here, and 1/4 of a circle. So it's not just any curve, it's a circular curve. So to find this area, we're going to have to think a bit outside of the box. I'm going to section off this space of land right here. I'm going to erase the green for a second. So the area bounded by these two black lines and this one orange line, and also of the x-axis, it's a square. It's a square. And this area right here is the area of a quarter circle. It's 1/4 of a circle. So if we wanted to find the area of this green portion here, we would need to take the area of the entire square. We would need to take this area. This is going to look a little sloppy. Minus the area of the semicircle. So just going to carve it out there. Something like that. And that would give us the exact area of the green segment. It did look a little messy, not how I wanted it to turn out, but you do get the idea. By taking the area of the entire square and subtracting it from the area of the semicircle, we get the green portion that we want. And so the square is a 3x3 square, and so we're just going to have that area be 9. Oh, excuse me. That's going to be 9. And we're going to subtract the area of the quarter circle. That's going to be pi r squared over 4. So it's going to be pi. The radius was 3, and that's going to be squared. So it's going to be 9 pi, actually. And this quantity over 4, and we're going to bracket that off. And now we're just going to go ahead with simplifying this. We're going to have 7 minus 2 plus 9 minus 9 pi over 4. And simplifying this down even further, we get -4 plus 9 pi over 4. Great. Now for 3b. we're going to evaluate this definite integral from from 3 to 5 of 2 times f prime of x plus 4 dx. So for this, we want to break this down a little bit further. Solving it in this state is going to be a little difficult. So you can split apart a definite integral if it's being added, if there's a sum inside of it. So I'm going to pull the 2 out. We're going to have this integral of f of x, f prime of x dx, plus the integral from 3 to 5 of 4 dx. Now we're going to have to employ some fundamental theorem of calculus concept. So I'm just going to write this out here on the side. This integral evaluated at the endpoint is going to be equal to the antiderivative of the upper bound minus the antiderivative of the lower bound. And we have the graph of f, so we can find these points relatively easily, excuse me. So this is going to be equal to 2 times f of 5 minus f of 3 plus, and this is just a simple power rule, or reverse power rule, 4x evaluated from 5 to 3. Now f prime of 5, that's given to be 0. And f of 3, that's a kind of hard point to pinpoint, but that's why in the stem of the question they give you, it is said that it is known that the point 3 comma 3 minus root 5 is on the graph of f. So f of 3 is equal to 3 minus root 5. And so we're going to use that in our question here. This is going to be equal to 0 minus, we're going to have a parentheses here, 3 minus root 5, close them both. And we're going to evaluate 4x from 3 to 5. So just doing that really quickly, that's 4 times 5 minus 4 times 3. And we're just going to simplify this out. I don't think you have to at this point. Once you have a answer that you can put into a calculator and it will yield out like a number answer, I think you can stop, but I'm gonna be honest, I don't really like how this looks, so I'm just gonna simplify this out really quickly. This is gonna be negative 3 plus root 5 plus 20 minus 12. And this is just going to redistribute that to negative 6 plus 2 root 5 plus 20 minus 12. And so our final answer is going to be 2 plus 2 root 5. Now for part C. The function g is given by g of x is equal to the integral from negative 2 to x of f of t dt. We're going to find the absolute maximum value of g on the interval negative 2 is less than or equal to x is less than or equal to 5. And we're going to justify our answer. So I see absolute max and I'm thinking take the derivative, find your candidates, do all of that process. So taking the derivative of g of x is going to involve a pretty easy application of the fundamental theorem of calculus. So just rewriting this out, g prime of x is going to be equal to f of x. And hey, that's the graph. So we want to find when our derivative is equal to 0, ergo when f of x is equal to 0, since that's our derivative of g. And we can find that pretty easily on the graph. We see that it's equal to 0 at negative 1, at 1/2, and at 5. I'm just going to write that out, negative 1, 1/2, and 5. And I'm actually going to make a sign chart to find the critical points. I do think that sign charts are extremely useful in calculus, but they don't serve as sufficient justification for a final answer. They kind of just help you organize your thoughts. So we're going to create this, with this being negative 1, 1/2, and 5. I probably shouldn't have put these little tail marks at the end because it is a closed interval, but we'll leave it for now. So at any point before negative 1, the function is shown to be positive. Then after negative 1, it goes from positive to negative. So I'm just going to put a negative value there. And then from 1/2, anything before that was positive or negative, and then afterwards it turns to positive. And then at 5, the interval ends, so we won't put anything there. So our potential max is at x is equal to negative 1 because it demonstrates a change from positive to negative. So now we're going to go on with the candidates test. We're going to test the endpoints and our potential max given from the critical point. So let's test g of negative 2. So we're just going to plug it into the original function, not the derivative function. So x is going to be -2, and the -2 at the bottom stays the same, f of t dt. And the property of integrals, if the definite integral, if the bounds are the same, then the area is 0 because you didn't move anywhere. There was no distance covered. This is going to be equal to 0. And now we're going to look at g prime of -1. This is equal to the definite integral from -2 to -1 of f of t dt. Don't let the t scare you. We're still looking at geometric area. So we're going to look at this graph from -2 to -1. We're going to focus on this triangle right here. It's going to be a positive area. It's going to be 1/2 times the base of 1 and a height of 1. So it's going to be 1/2. And now for g of 5. This is going to be the integral from -2 to 5 of f of t dt. Now this is just going to be the area of the whole thing, which we did find in a previous part of the question. Whoops. We found out the area of the whole thing in a previous part of the question. It was this part. The area of the whole thing is going to be this expression right here. It's going to be 11 minus 9 pi over 4. So I'll just write that right here. We don't have to redo the math again since we already did it before. And so now we have to look at which candidate yielded the maximum value when plugged into the original function. And it was when x was equal to 5. So just writing out a final statement for a little justification. The absolute max value of g on the interval, instead of writing it in the notation that they give there, I'm going to use parenthesis notation, or rather bracket notation because of that equal sign, is 11 minus 9 pi over 4. And we don't have to give further justification because our work here is the justification. We showed that we took the derivative, set it equal to 0, found all of our candidates, and tested them for the max value. Now for the final part, we're going to find the limit of this statement. So when tackling limits, we're just going to first just shove in the number that x is approaching and see if that works. And if it doesn't, we will adjust later. So we're just going to say that this is equal to 10 to the first power minus 3 f prime of 1 over f of 1 minus arctan of 1. So first, let's adjust this f prime of 1 portion. We want to find the slope of the graph of f when x is equal to 1. Now, thankfully, this is in one of our linear line segments. So we can just take the slope of this linear line and it'll apply to 1. So we're just going to do that off to the side. F prime of 1 is equal to, I'm going to focus on these 2 points. So it's going to be -3 minus -1 over 2 minus 0. And this slope is going to be equal to 2. And now we have this f of 1 here. And f of 1 is equal to 1. So I'll just write that again off to the side. And now we can do our adequate substitution. So 10 minus 3 times 2 over 1 minus arctan of 1. This is going back to some pre-calc days. We want to find the value of x that makes tangent equal to 1, and that x value is equal to pi over 4. So the value of arctan of 1 is pi over 4. And simplifying this down a little bit further, 10 minus 6 over 1 minus pi over 4. So you get a final answer of 4 over 1 minus pi over 4. You could simplify further, but this is the extent to which the scoring guidelines do, so I won't touch it any further. Now, number 4, we're more than halfway done. We have this stem talking about a cylindrical barrel, and I'll let you read that to just kind of digest it. And instead of putting the image again, I'll just have the text, which has the information relating to the image. And so we're going to find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet, and of course, indicate units of measure. So we're going to use this equation that they graciously gave us. They didn't have to, but they gave us it B is equal to pi r squared h. And we want to take the derivative of this because we're trying to find the rate of change. So we're just going to apply a d dt because we're finding the rate of change with respect to time of this whole thing. So related rates, implicit differentiation, they kind of go hand in hand. So we have dv dt is equal to, now I do want to mention that the only variables here are v and h. R is a constant. The radius of the cylindrical barrel isn't changing, the height is. So we're going to treat it as a constant when doing our whole derivative business. So this is going to be equal to pi r squared dh dt. That pi r squared is a constant multiple, so we're only focusing on the h, which when we take the derivative is dh dt. Now we want to find the rate of change of the volume of water dv dt when the height of the water is 4 feet. So now, well, actually, we're given that dh dt is equal to negative 1/10 root h, so I feel like that is an appropriate substitution to make, especially since we don't have a calculator. So we want to be kind of careful when plugging in our values. So now we're going to find dv dt when h is equal to 4. And so we have pi. The radius is given to us as 1 because the diameter is 2. Half the diameter is the radius. So that's just going to be 1 plus, or rather not plus, excuse me, minus 1/10 times the square root of 4. Simplifying this down a bit further, we have pi times negative 1/5, which is negative pi over 5. And we want to put units. So the units of volume are feet cubed, cubic feet per second, because it's the rate. So that's the final answer. 4b. And the height of the water is 3 feet. Is the rate of change of the height of the water with respect to time increasing or decreasing? So, and explain your reasoning. So when finding when a function is increasing or decreasing, we're going to take a derivative. So we're going to look at the dh dt portion. We're given that dh dt, it's in the stem of the question, so negative 1/10 root h, and we're going to take another derivative of this whole thing. So we're given that the second derivative of h with respect to time is equal to, now we need to be careful. We're going to take the derivative of this 1/10 root h. The derivative of root h is 1 over 2 root h. And so when you multiply that to negative 1/10, you're going to get negative 1 over 20 root h. This root h is in the denominator. And this is kind of like a mini chain rule. We're going to multiply this by dh dt because the derivative of h is dh dt. And we are given that dh dt is equal to negative 1/10 root h. So I'm just going to rewrite this down here. We're going to take this same portion that we found here, and we're going to multiply it by negative 1/10 root h. Now, this root h is in the numerator, and this one is in the denominator. So they're going to cancel out. Negatives also cancel out. This is equal to 1 over 200. And this is a positive number. So now we have to interpret this in the context of the problem. We're going to say that since the second derivative of h with respect to t is greater than 0, meaning it's positive. And I'm going to use the same wording that the problem uses. The rate of change of the height, I might run out of room, but the rate of change of the height of the water with respect to time, I'm definitely going to run out of space. I'll just make a little asterisk here, is increasing. That's our explanation. You want to have a little statement like that if it says explain your reasoning. Again, you don't have to like write a college thesis when doing it. A simple explanation supplied by work is fine, and that will give you full credit. 4C. At time t equals 0 seconds, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. This is probably the most involved section of this problem. I might have to use another page for this. I didn't allot myself another page, so I hope not, but worst comes to worst, I'll just add another page. So we're gonna, again, start with the differential that they give us. dh dt is equal to negative 1/10 root h. And with separation of variables, you want to separate these two. You want to have dh on one side and dt on another side. So that's what we're going to do right now. We are going to divide this dt on both, or rather, we're going to cross multiply. I should say cross multiply instead of divide. We're going to have dh is equal to negative 1/10 root h dt. And I want the h and the h to be on the same side because they have the same variable. So doing that really quickly, we get negative 10 over root h dh is equal to dt. Now here comes the part where we integrate. I'm going to take this negative 10 as our constant multiple, move it onto the outside, and I'm going to rewrite 1 over root h as h to the negative 1/2 to make our integration simpler when we do it later on. dh is equal to the integral of dt. Now just doing our simple power rules, we get our reverse power rules, we get negative 10 times h to the 1/2 over 1/2 is equal to t plus c. Now, you may be thinking, why didn't I add a plus c to the first integral? Well, technically, there should be a plus c here, but they're both constant. So if I subtract this plus c on both sides, a constant minus a constant is still a constant. So this plus c will absorb this minus c and still retain this constant value. So I actually don't have to show out this whole exchange. The AP Calculus readers will kind of just see through that and they'll just accept this with plus c on at least one side of the equation to kind of acknowledge that it's there. Now, I do think I'm going to need another page, so I'm going to add that really quickly. Now, we're going to simplify this a little further because we do want to express h in terms of t, so it's kind of a little chaotic now. This is going to be negative 10 times 2 root h is equal to t plus c, and we can sub in the negative 10, so we get negative 20 root h is equal to t plus c. Now, at this point, our math might look a little different. I personally like to sub in the conditions that we were given initially first instead of solving for h first. I just find it to be a little easier. So I'm going to sub in t is equal to 0 and h is equal to 5 as given to us by this portion of the question. So we're going to get negative 20 times root 5, because h is equal to 5, is equal to 0 plus c. So that c is equal to negative 20 root 5. Now, I do apologize for the layout of this page. It's not consistent with the horizontal layout, but it should still function for us. So we get negative 20 root h is equal to t minus 20 root 5. I do believe that's what we had originally. I'm looking right here. So negative 20 root h is equal to t, and we found c, and we plugged it in right there for that. Great. So now we're going to go through the process of isolating this h value. So we're going to divide by negative 20 on both sides. So we get the square root of h is equal to t minus 20 root 5 over negative 20. But I do want to take a step back and simplify this fraction just a little bit. I'm going to write this in blue because this isn't like necessary to a final answer, but I do think it is worth just kind of going over it. So with this fraction, we can decompose it to t over negative 20 plus negative 20 root 5 over negative 20. So obviously we can't do a lot with the first portion of that fraction, but the second one, these negative 20s cancel out. So this reduces to negative t over 20 plus root 5. And so I'm just going to express that in black here. We're going to rewrite this as the square root of h is equal to negative t over 20 plus root 5. And I'm going to just undo the square root by squaring both sides. So we get that h is equal to negative t over 20 plus root 5 squared. And that kind of addresses the answer to find an expression for h in terms of t. This would be our final answer. Again, I do apologize for the vertical layout. I did not allocate a separate page for this, as I thought I could do it all in one, but clearly I couldn't. So, but here's our final answer, and that is going to wrap up our question 4. So now we're going to move on to number 5. We're going to let R be the region enclosed by these two functions, the y-axis and the vertical line x equals 2, as shown in the figure above. That's our stem. And so our first task is to find the area of R. So I think it is appropriate to kind of label which functions are which. So we're given a cosine function, so a trig function, and a parabolic function. So we know that with cosine functions, or like really any trig functions, they're going to assume kind of like this waveform, whereas a parabola, it's going to be a negative parabola in this case, kind of just assumes this one big arc. And that's kind of what this graph right here is showing. It's kind of just the one big arc, whereas this graph on the bottom, it's kind of showing like a wave function. Like right here, it kind of indicates it kind of just wants to go up. A characteristic of a cosine function. So this top curve is going to be our h of x, and this bottom curve is going to be our g of x. And that's important when finding area, because when finding area, you want to take the integral from the specified bounds of the top function minus the bottom function. And so that's what we're going to do here. We're going to say that area is equal to the integral, and it's bounded by this line x is equal to 2. So that's where we're going to set our bounds to 0 to 2 of h of x minus g of x dx. Now, if this was a calculator portion, you would stop here, plug in the functions into your calculator, give a final answer, and then be done. But unfortunately, this is no calculator. So you do have to show out the process of integrating by hand. So we're going to say that area is equal to this, not the square root, to the integral from 0 to 2. And I'm going to literally plug in what h and g is equal to. So we have 6 minus 2 times x minus 1 squared, minus this whole thing is being negated, negative 2 plus 3 cosine of pi over 2x, and this whole thing dx. Now that's a lot. So I recommend kind of splitting this up into two different portions. I'm not gonna lie, I might have to use another page, which I really wasn't expecting, but here we are. We're gonna split this up into two sections because we can split up an integral if there's a sum or a difference inside of it. So this is gonna be our section 1, and this is going to be our section 2. So just focusing on area 1. Oh, I should establish the relationship that the total area is gonna be equal to the area 1 plus area 2, just so I don't have to write that out later. So now, let's focus on area 1. That one seems a little more basic because it's just algebraic concepts. It's just one variable, there's no trig, so let's do the easier one first. I'm just going to rewrite this as shown here, and I'm actually going to split this integral up so that I can take this negative out. So doing that, we get the integral from 0 to 2, 6 dx, minus 2 times the integral from 0 to 2 of x minus 1 squared dx. Constant multiple, I just took it out of the integral sign to kind of make my life easier. Now this isn't this doesn't look that bad. So the integral from 0 to 2 of 6 dx is just going to be 6x evaluated from 0 to 2 minus And this is a mini u sub, so doing this u substitution stuff out, we get that this is equal to negative 2/3 times, negative 2/3 times x minus 1 cubed from 0 to 2 as well. And now we're just going to go through the process of like evaluating that. We get 6 times 2 minus 6 times 0 minus, and I'm going to block this whole thing off so that like I can be more focused when doing my arithmetic, because unfortunately it is required here. So we're going to get minus 2/3 2 minus 1 cubed minus 2/3 0 minus 1 cubed. Now doing this math out, we get 12 minus 0 minus, and we're going to block this off again. We have 2/3 times 1 to the third power. So that's just going to be 2/3 minus, or rather plus, because the 0 minus 1 to the third power is going to be a minus, and the two negatives negate each other. So it'd be 2/3 plus 2/3. And so this whole thing ends up being 12 minus 4/3, and that's the area for this first blue section. Now we have to go on to the area of part 2. Now I again apologize, it's going to be another vertical page, which doesn't really look nice compared to the rest of the slideshow, but I do need more space. So now we're going to focus on area 2. Actually, I do think I can. Okay, that looks a little better. Not terribly. I think I can do that. Yeah, okay. So now we're going to take this side of the integral. Oh, I should mention that the area total would be A1 minus A2 because they're being subtracted. So I'm just going to adjust that little caveat. And so area 2 is going to be equal to this integral from 0 to 2 of negative 2 plus 3 cosine of pi over 2, or pi over 2x dx. And I think I'm going to do the same thing that I did with the last one, in which I'm just going to split it up to kind of isolate that trig component, because that's going to be the most troublesome part of this integral. Yeah, there's a reason this video is going to be really long, and it's probably like these later questions. So again, this first part of the integral isn't going to be that bad. It's just going to be a negative 2x evaluated from 2 to 0. And this part is going to be the one that's going to be a little more troublesome. We're gonna have to do a u substitution. So u is going to be equal to pi over 2x. The derivative of that is going to just be pi over 2 dx. We want the dx to be by itself, so we need to isolate that by getting rid of the pi over 2, and that will just be 2 over pi du is equal to dx. And I know that Rahsun does not like the way I do u sub, so don't tell him. But we're going to take this constant multiple out, and for this u, we're going to sub in the values of x for our bounds of integration into what u stands for, because now we're in the u world. So pi over 2 times 2 is just going to be pi, and pi over 2 times 0, that's still 0. And now we have 3 cosine of u du. And we're going to go ahead and further solve that, or further break that down, I should say. I'm going to still keep this as negative 2x from 2 to 0. And we're just going to solve this component of the puzzle piece. So this is going to be 2 over pi times 3 sine of u evaluated from 0 to pi. 2 pi, not the value 2 times pi. So we're going to go through the process of evaluating these things. We're going to have negative 2 times 2 minus negative 2 times 0 plus, I'm going to bracket this off again to signal that we're doing a different portion. We're going to have 2 pi times 3 sine of pi minus 3 sine of 0. And again, we're doing all this with respect to radians if you couldn't tell with the pi's. So this is going to be -4 minus 0 plus 2 pi, or 2 over pi times, well, sine of pi is equal to 0, 3 times 0 is 0. Sine of 0 is equal to 0. -3 times 0 is still 0, so this is going to be a plus 0. So this whole thing is just going to simplify to -4 because this product, 2 over pi times 0 is 0, and so it'd be -4 minus 0 plus 0, so it's just going to be a 4. And so that was our work for area 2. We found our area 1 here, and so now we have to go through the process of merging the two areas that we got together. So I'm just going to say that area total is equal to A1 minus A2. So we got that A1 is equal to 12 minus 4 over 3. And this is going to be minus 4 from our A2. And this is going to, or rather, minus -4. Because it's two negatives. And this is going to yield 16 minus 4/3. And if you wanted to simplify that further, that would be 44 over 3. And that would be the final answer to A, find the area of R. That was a very involved integration process. I'm not going to zoom in just so that you can see the extent of the work that we did. Yeah, that question was a lot. And so if you got through that, kudos to you. Now, part B. Region R is the base of a solid. For the solid at each x, the cross-section perpendicular to the x-axis has an area. A of x is equal to 1 over x plus 3, and we are asked to find the area of the solid. So this is kind of one of those things that tests your concepts, your knowledge of calculus in a way that isn't typical of the APA exam. You have to know that when you integrate an area function, it'll yield the volume over a certain interval, because volume is the accumulation of infinitesimally small pieces of area over an interval. So knowing that information, we can say that V volume is equal to the integral from 0 to 2, because that's where a region is bounded, of this function A of x that denotes our area. And so just subbing in what area is equal to, we have 1 over x plus 3 dx. Now, luckily, this integral is much easier to solve than the previous one. It's just a mini u sub, nothing too terrible. And the results of this is going to be ln of x plus 3. Make sure you have those absolute value bars. And this is going to be evaluated from 2 to 0. And so v is simply just going to be ln of 5 minus ln of 3. That's the volume of the solid. And now we're on to 5C. Write, but do not evaluate, an integral expression that gives the volume of the solid generated when R is rotated around the horizontal line at y is equal to 6. So y equals to 6 is, I just want to see where it is. 1, 2, 3, 4, 5, 6. It's the last tick mark. And so that seems to be above the region, and that's where we're going to be rotating. So it looks as though this is going to be a washer. I know the pen length that I'm using right now is kind of thick. This region is going to be below this axis of revolution, and it doesn't actually touch. So this is going to be a washer. And when the axis of revolution is above the shaded region, I do think this is important enough to write in our blue pen. It's going to be denoted by pi from A to B, wherever the bounded region is. And we're going to have the horizontal line y minus the function. So this time it's going to be g of x squared minus, again, the horizontal line, minus the function h of x squared dx. Now, you may be thinking, why did I put g of x first, where when we were doing area, it was h of x first? Well, the furthest function from the axis of revolution is always going to be the first of the integrand when dealing with washers. And so we've established that this function right here is h, and this function is g of x. And so this distance right here is much greater than this distance here. So we're going to use g of x. And now we're just going to plop in the appropriate numbers so that it works. And we don't have to evaluate this. We're going to write the integral expression and then be done. So this is going to be pi from the integral of 0 to 2. And our y value is 6. We're given that it's 6. So we're going to say 6 minus g of x. I'm not going to write that monster of a function again because I don't have to evaluate this. So I'm just going to write it as g of x. And same thing here, 6 minus h of x squared dx, and you're done. That's the question. Now for the final question. This is not a long stem, but I do find this question to be quite tricky if you are caught off guard. So we're going to find h prime of 2. So this is kind of a gimme because you're given the tangent line, y equals 4 plus 2/3 x minus 2. And obviously the slope of the tangent line is equal to the derivative at that point. And so the slope of this is 2/3. So h prime of 2 is equal to 2/3. Kind of an easy question after long, laborious tasks of question 5. Now B, we're going to let a be the function given by a of x is equal to 3x squared times h of x, and we're going to find the expression for a prime of x, and then find that derivative evaluated at 2. So this question is kind of just testing your knowledge of the product rule. So we're going to let a prime of x be equal to, we're going to let it be equal to the derivative of the first portion. That's going to be 9x squared. And we're not going to differentiate the second one just yet. Plus, and now we're going to take the normal first, 3x cubed times the derivative of the second portion, h prime of x. And that's going to be our expression for a prime of x. And now we're just going to evaluate this at a prime of 2. So everywhere that you see an x, we're just going to sub in a 2. This is going to be 9 times 2 squared times h of 2 plus 3 times 2 cubed times h prime of 2. So this kind of just simplifying this down, we get 36. We see that h of 2 is 4 from the question stem, plus 24. And this is going to be equal to 2/3 from what we found in the previous question. And this whole thing is going to simplify to 160. Again, I believe that you can stop once you get here because this is an answer that you can plug into a calculator and get 160 from, but I don't think the simplification is that bad. So if you're in a position to do it, just go for it. Now 6C, this one is a doozy. So we have the function h satisfies h of x is equal to that for x is not equal to 2. And it is known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. So we have to use that limit to find f of 2 and f prime of 2, and we have to show the work that leads to your answers. So again, I came unprepared. I'm pretty sure this will require a new page, so let me just do that right now. And so we're going to start here, obviously, but we have to understand a couple of things before we go on with answering this question. So it is given to us that h is differentiable. So it's twice differentiable actually, but we'll just focus on the fact that h is differentiable like just once. So h is differentiable, which means that h has to be continuous. H is also continuous. Differentiability implies continuity. So you need to explicitly state that out. And what that means is that the limit as x approaches 2 of h of x is going to be equal to h of 2. And so now we can use that when finding f of 2. So we can say that this limit statement, the limit as x approaches 2 of x squared minus 4 over 1 minus f of x cubed, this whole thing is going to be equal to 4. It's equal to a number value. And so now we're going to do what we do with limits. We're just going to sub in x equals 2 and see what happens. So when we sub in x equals 2, we get 4 minus 4 in the numerator. And we get 1. Or rather, actually, I want to take it back, just a step back. I want to express this as the limit as x approaches 2 of x squared minus 4 over the limit as x approaches 2 of 1 minus f of x cubed. I feel like this will help us understand later parts of the question a little better. And that's really what this statement is saying. It's the limit of both the numerator and the denominator evaluated. So now going on with our simplification, this is going to be 4. Or rather, that's going to be 0, I should say, because 2 squared minus 4 is 0. And we don't know the value of f of x. That's what we're trying to find, or f of 2, I should say. But we know that this bottom portion has to be equal to 0. It can't be equal to anything other than 0 because we know that the limit exists. So let's say if this bottom portion was like equal to 1, that would just lead to a limit that doesn't exist, which is nonsense. We know that it's equal to 4. And so that means that this limit has to be some sort of indeterminate form that can be evaluated later using L'Hopital's rule, which is exactly what the question says. So the denominator must be equal to 0 so that this limit statement assumes the indeterminate form that L'Hopital's rule can be used in. And so now we've made the explicit relationship that limit as x approaches 2 of that function is equal to 0. And so we're just going to take this to another page. I know, I apologize. We're going to say that the limit as x approaches 2 of 1 minus f of x cubed is equal to 0. And from this, we can say that the limit as x approaches 2 of f of x is equal to 1. And we are given here that f is twice differentiable. So again, we say that since I'm sorry, I have to adjust this. Since f is differentiable, at x is equal to 2, it is also continuous there. So with this statement, we can make the explicit relationship that the limit as x approaches 2 of f of x is equal to f of 2, which is equal to 1. Now, unfortunately, that is not the whole question. We also have to find f prime of 2. So now finding f prime of 2, we have to say a new relationship. This is why they give you that h is twice differentiable. So we have to rewrite that. We have to say that h is twice differentiable, meaning that the function, I'm not going to write the function, but meaning that h prime is continuous as well. And so again, we're going to write out the statement that the limit as x approaches 2 of h prime of x is equal to h prime of 2. This is kind of like the equation that solidifies this continuous notion of a function. So now we have to find the limit as x approaches 2 of h prime of x. And we're going to go through that process here. And to find this, we're going to go back to what we were given and take the derivative of the top, take the derivative of the bottom. This isn't like a quotient rule. You're taking the derivative of the numerator and denominator independently and just placing that into a new fraction. So going over that, we get that. The numerator isn't that bad. It's just a simple power rule. So we just get 2x. The denominator is a bit more involved because you have like a chain rule. So we have -3 times f of x squared. And this is where the chain rule comes. We have f prime of x. And we know that this whole thing is equal to 2/3. Because we saw in the first or in the first part of the question, h prime of 2 is equal to 2/3. And so now using this, we're just going to sub in what x is equal to when x is equal to 2. So we have 2 times 2 in the top over -3 times f of 2 squared times f prime of 2. and we're going to have this whole thing is equal to 2/3. We're going to simplify this down a little bit. We know that, I'm going to do the denominator first. We know that f prime of 2 is equal to 1 from above. So this is just going to be -3 times 1 squared. We don't know what f prime of 2 is, though. That's what we're going to try and find. This denominator, or rather this numerator, is going to be equal to 4, and this whole thing is equal to 2/3. And now we can do some cross multiplying business. We can cross multiply like that. I'm gonna erase that though. We have -6. F prime of 2 is equal to 12. And again, getting that out of the way, we get f prime of 2 is equal to -2. So that's where we found f prime of 2. And that is our final answer. We found both f and f prime of 2. Yeah. Okay, now for 6D. It is known that g of x is less than or equal to h of x for 1 is less than x is less than 3. Let k be a function satisfying g of x is less than or equal to k of x is less than or equal to h of x for 1 is less than x is less than 3. Is k continuous at x equals 2? And we're asked to justify our answer. So we know that the functions g and h are continuous because they are known to be differentiable. So I'm just going to write out the statement that the limit as x approaches 2 of g of x is equal to g of 2, and the limit as x approaches 2 of h of x is equal to h of 2. So our objective is to prove the same concept, but for k. We want to find that the limit as x approaches 2 of k of x is equal to k of 2. And so we're going to use this initial kind of inequality statement and this initial inequality statement and apply limits to them. Because 2 is within the interval, we are in the boundaries to say that the limit as x equals 2 of g of x is less than or equal to the limit as x approaches 2 of k of x, which is less than or equal to the limit as x approaches 2 of h of x. We basically just applied a limit statement to all of these three portions of the inequality statement, and now this should look familiar to you as the squeeze theorem. And we've already established that the limit as x approaches 2 of g of x is 4. And we know that the limit as x approaches 2 of h of x is also equal to 4, which means that the limit, I should write this down a little nicer. The limit as x approaches 2 of k of x has to equal 4 in order for this inequality to work. So we can explicitly state this out here. Now we can go back to this original inequality statement. I'm going to write it out again. And we know that g of x, or rather g of 2 is equal to 4. We're going to let x equal to 2, so k of 2. And h of x is also equal to 4, which means that k of 2 has to be equal to 4 for this statement to be true. And so since k of 2 is equal to the limit as x approaches 2 of k of x, and they're all equal to 4, you don't have to add that, k is continuous. And that's it. That is the final portion of this FRQ. This was really long. That will conclude it though. If I made any mistakes, I will be sure to let you guys know in the comment section, because it is possible that I did, but I did really try my hardest, the best of my ability, to explain all of these questions as I did. So if you guys are left with any questions, please leave them in the comment section below. Again, I hope that the timestamps in the description were useful to you so that you can kind of like pinpoint where it is you need help. And one final tip for the free response questions when you're on exam day is that really with calculus AB, the two major functions that you learned is to differentiate or integrate. So if you don't know what to do, Just take the derivative or take the integral, and chances are it'll lead you somewhere. You just have to be engaged with the question. Please don't try and don't let your mind wander. Do something or move on if the question is stressing you. I do appreciate your time here, and I hope you have a wonderful day.